Here's a fun fact. There aren't many reliable ways to mesh a point cloud with a watertight manifold surface. Unless, of course, you have an oriented point cloud, but without normals, it's much harder to do so. Colleagues at my alma mater have been developing finite volume diffusion methods for image processing and other interesting applications. As an excited graduate student who was intrigued by differential geometry and graphics, I walked into my supervisor's office with a desire to work on surface remeshing, only to be offered an unconventional idea of remeshing by shrink wrapping. We would start with a surface of higher quality, hoping that tuning in the relevant parameters would do the job of improving the overall surface tessellation quality. It seemed like a manageable amount of work for a master's thesis for a few months. Now, 3.5 years later, I've learned that manageable in academic language sometimes means good luck, see you in a few years. The method itself actually turned out to be a quite versatile automatic tool for extracting shapes from voxel mesh and point cloud data, provided that we integrate combinatorial changes via adaptive remeshing. This is, of course, drastically improving the reconstruction quality. Compared to previous iterations of the reconstruction tool, we use trilinear interpolation instead of the nearest neighbor approach for pointwise values within the data's distance field. We also extended the scope of possible starting surfaces to allow shrink wrapping higher genus target data. The evolving surface mesh quality is evaluated using our adjusted triangle quality metric to determine when remeshing is necessary. And lastly, we utilize curvature-based feature detection techniques to preserve the important features of target data. To put our work in its scientific context, a crucial component of the evolutionary methods lies in the phenomenon of surface varying, which can be simply defined as shape simplification by optimizing some energy functional, like Wilmore energy by Crane and colleagues, the Dirichlet energy by Professor Mikula and colleagues from the Faculty of Civil Engineering in Bratislava, and so on. Crane's lab then continued their work in repulsive surfaces, which untangle from more complex knot-like shapes by Yu and colleagues, also first calling such evolutionary process shrink wrapping. A similar technique is later used by Zocht and colleagues for so-called nested cages. The team of the Faculty of Civil Engineering later worked on point cloud reconstruction using their earlier 2014 evolutionary model equipped with advection. To also mention the latest advancements in point cloud reconstruction using shrink wrapping, Rana Hanoka and colleagues developed a neural network for point clouds which can also predict missing data. Because shrink wrapping in essence ignores internal cavities and other unnecessary data, it is also used for mesh simplification by enveloping CAD models by Hurtado and colleagues. A natural consequence of this technique is also its hole filling aspect. Interestingly, the use of evolutionary mesh processing methods dates back to the beginning of this millennium, with Stephen Smith laying the foundation for the brain extraction from CT scans, yielding a widely used tool in neuroscience. And lastly, the idea of using projection-based analog of shrink wrapping for remeshing dates back even earlier, but generally it comes with essential limitations in the resulting mesh quality from distortions. This was improved by another paper from the civil engineering colleagues Medla and Huska, who remeshed by outward evolution of decomposed surface patches. In our work, we evaluate the applications of point cloud surface reconstruction and enveloping mesh simplification. The mathematical model is governed by a nonlinear partial differential equation for a surface immersed in Euclidean space. Its primary term is the weight mean curvature flow doing the actual shrinking. Then there's advection driven by scalar distance field and its gradient. And the tangential movement is governed by an angle optimizing redistribution law introduced by Huska and colleagues. The control functions of the three terms are the complementary Gaussian target detectors, which are zero when the surface approaches the target set gamma, and the advection function computing the influence of the negative gradient of the distance field. This function also rotates the surface so that its unit normal evolves towards parallelness with the gradient. This has the effect that the surface evolves inward into concave regions and attempts to fully wrap the arbitrary target set. This equation is then discretized using a cotangent Laplacian finite volume scheme into a sparse linear system, which is then solved by a bi-CG step solver for each time step. We can start with any reasonably discretized starting surface, such as an icosphere enveloping the target, a Marching Cubes isosurface, which is remeshed for better quality, and also a remeshed convex hull surface, which directly preserves the feature convex hull vertices. Since we're computing all time steps numerically, there are constraints for the stability with regards to the surface discretization. We follow a rule that for a semi-implicit formulation on a mesh surface, we want to ensure that the time step size is approximately equal to the square of the spatial step. On a triangle mesh, this translates to the measure of the barycentric or Voronoi volume element around each vertex. To ensure the stability, we want to make sure the spectral radius of the system matrix is below 1. And the most straightforward solution to this is to compute a scaling factor for the surface so that its elements are approximately equal to the time step size. The scaling factor can be derived from the approximate equality itself by assuming, for example, a uniform distribution of points on a spherical surface with radius r. For an evolving isosurface, the approximate covolume measure can be computed by estimating across 4 neighboring voxels. The scaling factor needs to be adjusted so that it corresponds to the covolume measures for all vertices across the majority of time steps to avoid instabilities. To ensure stability as well as triangle quality, we use a remeshing algorithm, which relies on a number of steps, starting with splitting edges longer than the given multiple of the target sizing, collapsing edges shorter than the multiple of sizing, edges flipping to equalize valence imbalance, and tangential relaxation without any combinatorial changes. Finally, this process can be finalized by reprojection to the original surface. These 5 steps are usually repeated during one remeshing procedure, for example 3 or 5 times by default in our experiments. For our algorithm, we use an improved approach by Duniak and colleagues with adaptive sizing. The unfortunate consequence of the adaptive remeshing algorithm is that it shifts the surface immersion into a slightly more smoothed representation. For this reason, we must take measures to preserve surface features, that is, subsets carrying essential shape information like ears, limbs, etc. For this, we use a curvature-based heuristic, namely a vertex is feature if and only if its angle of curvature is below a critical limit. To make things a little more complicated, the evolving surface may have false positives during shrink wrapping in the form of so-called convex dominant saddle points. Those are vertices where there's a large amount of imbalance between principal curvatures, with the positive curvature dominating in absolute value. The color map shows the point evaluation for the wrapped bunny mesh with a smaller ratio k. This turns out to be a helpful technique for preserving features by freezing the feature vertices against remeshing, which of course sacrifices mesh quality, so ultimately there's a trade-off. Now we can compose the overall algorithm from its individual steps, starting from one of the 3 chosen initial surfaces with properly tuned remeshing parameters. And another helpful step is the edge length sizing adjustment for some time steps by a given factor. This leads to a more detailed tessellation when the surface is closer to the target. So let's move on to the results section of this presentation. First, let's evaluate how the scaling heuristic for numerical stability works and whether we should tweak it or not. For 4 different regimes of the algorithm, we observed that the distribution of covolume measures stabilizes to around 1/5 of its original sizing, and also that remeshing helps in reducing the overall variance. This means we can choose a shrink factor parameter equal to 1/5 because most of the time the surface elements are 1/5 of their starting size. Furthermore, in our previous work, we evaluate the stability regions in the time step/scaling factor domain. We consider an evolution stable if it doesn't explode outside of its bounds too much. We can then conclude that the scale-based heuristic stabilizes the evolution reliably, while large deviations from the mean co-value measure introduce instabilities. Now we compared the performance of our method as a point cloud reconstruction algorithm with two related implementations by Daniel and colleagues, and the work of Yu and Crane from 2021, based on a different principle of minimizing tangent point energy. Just to recap, our experimental setup relies on our advection diffusion model with tangential redistribution, where we distinguish between two primary configurations: an obstacle, which produces minimal surface membranes similar to those of Crane and Yu, and the full wrap configuration, which completely wraps the target point cloud. First, we evaluated a simple in-radius-circumradius triangle quality metric from MeshLab, where we see a huge improvement of our obstacle configuration against Daniel and colleagues' result. And now we utilize our custom equilateral triangle Jacobian condition number quality metric, which also shows better histograms comparable to the technique by Yu and Crane, which also internally remeshes for some time steps. In the proceedings article, you can also find the distance-based histogram evaluation, as well as the evolution of an approximation of the surface to point cloud Hausdorff distance, which shows that our method is superior to the tangent point energy approach by Yu and Keenan Crane. The last insightful comparison is with the enveloping CAD surfaces by Hurtado and colleagues, who actually integrated their framework into Rhino. We compared their implementation with our isosurface shrink wrapper approach, useful for complex non-manifold target data with internal cavities, and we saw that it still needs some improvements, mainly by abolishing the use of isosurfaces and sticking to the convex hull or icosphere starting surfaces because of the inability to get rid of internal cavities. So, to make our algorithm work for higher genus arbitrary mesh or point cloud target data by first starting with a zero genus sphere or convex hull, we need to perform surgery on the self-intersecting evolving surface. This will be the topic of our future work, in which we will combinatorially remove the so-called pinched or inverted surface patches, because the simple deletion and hole filling is insufficient to properly reconnect the remaining triangles around the self-intersection polyline. And here's a sneak peek of an interesting application of our algorithm as a point cloud meshing tool used in the so-called incremental mesh builder for opening super large mesh files. In our future work, we state that there is no need to wait while processing the whole 3 GB file and then simplifying it. Instead, we just randomly sample some vertices using a well-chosen probability distribution across multiple threads, processing file chunks, and progressively stream the data to the application for meshing. In this evaluation, we can also see the performance of the optimized version of our shrink wrapping doing its job within a few seconds in consecutive LOD steps. We still have some way to go with making it fast enough for progressive loading applications. So that will be all from my side. Thank you for listening. I know it was a bit concentrated, but I'm ready for any questions if they arise.